Welcome, guys. Good to see you today. We're going to do something a little bit different today. We're going to do a video. So we're going to be doing Lesson 13, Module 1 right now. I'm going to go over exercises 1 through 5. We're going to be pausing throughout the video, so make sure you are taking notes. I will give you about 30 seconds to copy down each question, but I also want you to try it first, so I will be pausing. So just be ready. All right, let's get through this. Exercise 1. It says, the Fornax dwarf galaxy is 4.6 times 10 to the power of 5 light years away from Earth, while Andromeda 1 is 2.430 times 10 to the power of 6 light years away from Earth. Which is closer to Earth? So I'm going to go ahead and draw this out. Let's say this is Earth. Andromeda is over here, and then Fornax dwarf galaxy is over here. This is a dwarf one, and this is the Andromeda one. Okay. Dwarf one, it says, is 4.6 times 10 to the power of 5 light years away, and the other one is 2.430 times 10 to the power of 6 light years away. Remember, light years is a distance, like feet, or kilometers, or centimeters. These are all distances. It's not a speed, and it's not a time. Light year is a distance. It's the distance that light travels in 1 year. Okay, so this many light years away is the dwarf galaxy from Earth, and this many light years away is the Andromeda galaxy from Earth. So we don't know the exact distance from Earth that it is. I mean, it's a 3D dimension. So I'm just going to do this distance, and this distance. And then let's compare it. So I want you to think right now, I'm going to pause it, which one is closer to Earth? That's what the question is asking. Which one is closer? Okay, let's go ahead and pause. Okay, which one is closer? So we're going to pay attention to two things right now. First, we're going to look at the exponents of 10. Right? We know a is less than 10, so we're going to focus on the powers of 10. We see the power of 10 on the Andromeda galaxy is larger. It's further away from Earth as a result than this one. 6 is greater than 5. The power of 10 is greater than this power of 10. So we know this one is further. But it's asking which one is closer. So this one would be closer. The dwarf galaxy is closer. Okay. If they were the same powers, we would look at the next thing, which is the exponent, or the a, right? Remember I used to have the scientific notation up here written? Well, a would be the second thing you would look for. Okay. And whichever a would be bigger would be the one that is further away. But powers already worked. We found one that was greater, the power, so we checked that one out, and we saw that Andromeda was further and dwarf was closer. We're going to go on to exercise 2 now. All right, exercise 2 says, the average lifetime of the tau lepton, it's a type of molecule, I guess, is 2.906 times 10 to the negative 13 seconds. And the average lifetime of the neutral pion is 8.4 times 10 to the negative 17 seconds. Explain which subatomic particle has a longer average lifetime. Which one lasts longer? So each particle only lasts a certain number of seconds, and then they, I guess, turn into something else. I'm not really sure what happens to them. You can ask Mr. Boone about that one, because you guys are learning about particles, subatomic particles. Okay, so the tau lepton lasts 2.906 times 10 to the power of negative 13 seconds. So we're talking about time right now, not distance, not speed. We're talking about time. And the pion lasts 8.4 times 10 to the power of negative 17 seconds. So the question is, which subatomic particle has a longer average lifetime? Is it the tau or the pion? Which one lasts longer? Okay, I'm going to go ahead and pause and let you guys think about that. Okay, so let's look at it. Again, we're going to look at two different things. We're going to look at the powers first, and then if the powers are the same, then we would check out A. Okay, so let's check out the powers. We see that 10 to the negative 17 is smaller than 10 to the power of negative 13, and so this one will last less. So it's asking which one lasts longer. This one is greater than this one because the exponent is larger, right? Negative 13 is larger than negative 17. Think about it on the number line. Negative 17 is right here, negative 13 is right here, and 0 is right here, and here's the positive numbers. Negative 13 is larger, it's closer to positive infinity than negative 17. So we know 10 to the power of negative 13 is larger. So we don't have to worry about A. We already know that tau will last longer, more seconds than pion, even if it's significantly small. All right, let's go on to exercise 4. We're going to go back to 3 in just a second. Let's go on to 4 and 5 first. Exercise 4 says, compare 9.3 times 10 to the power of 28 and 9.2879 times 10 to the power of 28. So let's go ahead and compare those two. 9.3 times 10 to the power of 28 and 9.2879 times 10 to the power of 28. Okay, again, we're going to look at two things. First, the powers, and then the A. Okay, what's going on with the powers? Yeah, they're the same, right? Okay, so we're going to move on to the A because we can't compare powers that are the same. They're the same. No comparison, right? Neither one is greater or less than the other. Let's look at the A's. Which one is greater? Go ahead and shout out 9.3 or 9.2879. Okay, I'm going to give you a countdown from 3, and I want you guys to all shout it out in unison. Okay, shout out your answer in 3, 2, 1, go. Good. All right, yes, it was 9.3. That is greater than 9.2879. Okay, you can round this to the nearest tenth, and then you would see this would actually make it larger. Okay, but originally, this is smaller. And it is 2/100ths smaller than 9.3. All right, number 5. I think you guys can do this one on your own. So I'm going to give you some time to think about this. Let me just read it for you. Chris said that 5.3 times 10 to the power 41 is less than 5.301 times 10 to the power 41 because 5.3 has fewer digits than 5.301. Show that even though his answer is correct, his reasoning is flawed. Okay, the process is more important than the answer. I want you guys to explain the process. Show him an example to illustrate that his reasoning would result in an incorrect answer. So give me an example where if you used Chris's reasoning, we're just looking at the A's, right? If we're just looking at 5.3 versus 5.301, that his answer would actually be incorrect. That 5.3 times something would actually be bigger than 5.301 times something. Okay, so show me an answer right now. I'm going to go ahead and pause it, and then I'm going to show you my example. Okay, welcome back. So we have 5.3 times 10 to the power of 41. This is the original answer. And 5.301 times 10 to the power of 41. You can see how the powers of 10 are the same. But the A's, this one is slightly bigger. See how it has the same number plus some extra digits. So we say this one is larger. So Chris compared A's, but he didn't mention the powers, right? What if, and here's my example of how this one could actually become greater than this one, we change this power to something even just a little bit larger, like 42, 10 to the power 42, versus this number times 10 to the power of 41. Okay? So this one would then be bigger. All right, let's go over the exploratory challenge. I hope you had some time to work on it. If not, I'm going to go ahead and pause the video right now. Okay, let's talk about the exploratory challenge. So, given the two positive numbers, we're only talking about positive numbers now, okay, no negative numbers. Given two positive numbers in scientific notation, A times 10 to the power of m and B times 10 to the power of n. If m is less than n, then, and this is what I want you to prove, that A times m to the power, or A times 10 to the power of m is less than B times 10 to the power of n. Okay, so let's prove this statement right here. That A times 10 to the power of m is less than B times 10 to the power of n. Okay, we're going to prove this statement right here. We know one thing, that n is less than n. So this one is going to be less than this one, the exponents. Okay, so let's assume, I'm going to play devil's advocate. It means we're going to go with the most craziest example. Okay, we're going to start with the craziest example. Assume that A is greater than B, right? We're going to assume that A is greater than B. In fact, we're going to look at the craziest example, that A is equal to 9.9 with a replicand over it, and B is equal to 1. So the B is the smallest case, A is the largest case, right? Remember, A and B cannot be greater than 10, not including 10, and they can't be less than 1. So these are the most craziest cases. Okay? If this is the case, then that means that 9.9 times 10 to the power of m will be less than 1 times 10 to the power of n. We want to prove this now, right? I'm just changing A and B with our craziest cases. So we're going to test the most absurd case, the largest case. If this one works, any case will work, right? Okay, so let's prove this now. We know that m is less than n. Okay? So we know that m is less than n. So again, I'm going to show you the craziest case. Let's assume that if 10 to the power of m is going to be less than this one, we know that 10 to the power of m is going to be, or m is less than n. So let's assume that m is actually just equal to n, and n is just 1 more than m, right? The very minimum case. The only way that m and n could still be, that m could still be less than n, the most minimum case is that m is just 1 less than n, right? We know that m is less than n. If n is, let's say, 4, n, the very smallest case would be 5, right? Any less than that, and this would not be true. If n was 8, the smallest case would be 9. So the very minimum case that we have to test is that n is 1 more than n. Okay, so we're going to try this out. We're going to prove this. The most minimum case. Let's assume this. That means, so let's modify our proof again. 9.9 times 10 to the power of m less than 1 times 10 to the power of n if this is the thing that we're assuming, m plus 1 is equal to n. Let's change n into this. Okay, so 9.9 times 10 to the power of m is less than 1 times 10 to the power of, instead of n, I'm going to put m plus 1. Okay, let's prove that this is true. 9.9 times 10 to the power of m is less than 1 times. And here's the coolest trick right here. 10 to the power of m plus 1. We know that when we have exponents with the same base and we were multiplying them, we add their exponents. So what would be the reverse of that? That's right. It would be two exponents multiplying each other with the same base, and it would be so that if we were multiplying them, they would add their exponents. So the reverse would be 10 to the power of m times 10 to the power of 1. Right? Going from here, the reverse would be this. And the reverse of this would be this. Okay. Now we have this. Let's go ahead and divide both sides by 10 to the power of m. Make it more simpler. And we're left with 9.9 is less than 1 times 10 to the power of 1. 10 to the power of 1 is just 10. 10 times 1 is 10. Is this case true? Is 9.9 always less than 10? Is it? Give me a thumbs up if it's true. Give me a thumbs down if it's not. Yeah, it's always true, right? 9.9 is always less than 10. So, you guys know my little done marker, we have proved that this is always true. We have proved that a times 10 to the power of m is always less than b times 10 to the power of n if m is less than n. So now we proved that for all cases. Good job, guys. See you later. Thanks for watching.